So I've been asked to still talk about black hole binary formation, but things in the field. I find it a very funny way to say it, but I think I'll come back to that. And to skip the classic channel, and I'll interpret that a bit freely. Before I start, I would like to acknowledge many people that I collaborated with over the years, and the people in color have explicitly contributed to the thoughts that are here. Well, this picture you all know, you have seen it a million times, but I want to start from here, right? This is where we were. This is the black holes we knew about. Black holes that were observed in X-ray binaries. And then this happened. And we were all shocked, right? So this first event was so much more massive than the black holes that we knew so far. And then some of us panicked, and some of us, in different ways, some of us panicked and thought about very wild things. Others of us panicked because we really wanted to write down our paper that made such black holes, and others said, so what? I've always made 30 solar mass black holes. And so it was not the first, I mean, it made an even more massive black hole, but this is the picture that matters for binary evolution, right? These are the black holes that we think are the result of the endpoints of stars. At least I think that. I'm not going to do more exotic scenarios today. Maybe never in my life, actually. This is the rest of the family of black holes that we know now, with the ones they merged into. And so this is the picture that stellar evolution apparently makes. So I'd like to take you back in time for a moment and get some perspective of timescale. So let's go back to September 14, 2015, when the signal arrived at Earth. And so where did the signal come from? So that was the detection. And so for 1.4 gigayears, this traveled through space. And so this was a galaxy that was not too close, but relatively close. The reach of the detectors was not that much. And that's where the merger happened. But even before LIGO and Virgo and all the follow-ups have an enormous reach where we can go to different redshifts, we're already learning about very different redshifts. And that's because these black holes took a very long time to spiral in together. And probably several gigayears, depending a bit on the scenario that you want, but most of them, it's several gigayears. And so what I'm interested in is this last bit of time, which only takes a few million years, is what did the stars do to end up as these black holes? And so, even though we are only probing the local universe today, we're already probing the endpoints of stellar evolution throughout a very large portion of the universe, possibly one of the possibilities that they come from POP3 stars. I will not put my money on that, but I would think the first black holes came from a redshift 4-ish, something like that. It's probably not the peak of star formation, as was claimed in one of the first talks this morning, but it's probably the peak of metal-poor star formation in the case of black holes, which is probably a bit earlier than redshift 2, right? And so to put it in perspective, that's where we are. We don't have such a high reach, but we're probing black holes that were formed out throughout a major portion of the universe. And of course, we can do wilder things and think of them as primordial black holes, but that's not for this talk. So this is what I mainly study. How do these stars interact? And they can do many things. I work together with observers that try to determine how often do we find massive stars in the binaries, how wide are they, what are their mass ratios. And so one of the points that is very interesting for us, this is not very exotic. The majority of massive stars are found in systems that will do something like this during their life. 70% according to our studies, but most people agree that it's roughly half or more of that order. And that is shown in papers before and after. And so these are studies of star-forming regions very nearby where we can actually see the stars individually and measure, infer their masses and their periods. And that's what we need if we start to simulate these systems, right? This is the starting point from these simulations. One thing to keep in mind is that we can only do this in our galaxy or maybe the Large and the Small Magellanic Cloud at best. We have not done it in the Small Magellanic Cloud yet. Somebody gives us a large ESO program or to continue this study in the Small Magellanic Cloud, but in principle we don't know if the conditions that we take here, if they also apply to the earlier universe and to star-forming regions in starburst galaxies with redshift 4. We don't really know. But I don't think this is our main worry. Our main worry is still the physics. And so you can play a bit here. You can play factors of a few here, but we can play orders of magnitude still in the physical assumptions. So the left is not exotic. Most stars are in binaries, but these black holes are exotic. Well, soon we will be having many detections a year. but it's just a small fraction of the stars that make them. And so the interesting question is this, right? So what does it take for two stars to end up as binary black holes, and what is all the other interesting things that they make from it? And so what can we learn by looking at these black holes about all the other things, right? If we this 0.1% of the richest people, what do they tell us about the rest of the population? That's not entirely clear. Maybe it's such special, maybe it's such special conditions that these form that they're not helping us to understand stars at all. I don't think that's the case. I think we can learn a lot of interesting things about stars this way. Good. Formation channels. So I'll double a little bit what Ilya already did. I am less entertaining today. Usually I bring oranges to do this. I should have done that to beat his story about stars. But let's repeat this for one moment, right? So why is it so hard to get two compact objects so close? Ilya made this point well. I would like to state this as two challenges. One is the challenge how to get them so close. And if you want them to be black holes, how do you keep them massive while doing that? And so these are sort of mutually exclusive. And so these two circles would be to scale two stars, two massive stars, when they're very young, when they're burning hydrogen. And so I scaled them back to this size. Let's pretend it's the size of an orange. Then over the lifetime, these stars typically would stay this close, roughly. But both these oranges, they would roughly want to be as big as, what would be? Yeah, I think up to the ceiling or so during their lifetime. And so putting these two stars so close together, but both of these stars wanting to be that big, these stars are indeed going to merge, but way too early, right? They will merge when they're still stars, not when they're two black holes. And so the first challenge is how do you don't merge them too early? So we can't put them this close at the start, at least that was the main idea. And so, yeah, here it's to scale. So actually this is to scale, but I had to move the center of mass of this star to even help you see the other star. And that's not happening, right? The center of mass is still there. So these two stars are fun. They just became one new star. Also interesting, but not for gravitational waves. And so if you do this, there's no other way than that these stars interact and exchange mass and probably throw out a lot of mass. And that's probably not what you want if you want them to end as binary, as two black holes and be very massive. If you want them to end as neutron star, you have some mass to play with, probably. But so how do we do all this and avoid mass loss? And so every formation channel that I've seen so far, or I can think of, they have some way to overcome this mass challenge and this separation challenge. And so traditionally, there were sort of two areas, and you can still see in the program that these are the two areas. So the left is what some people call the field. I think evolutionary channels would be a better description. And tomorrow, people will talk about the dynamical channels. And the reason that this division is there, I think, is mostly by training of the scientists that work on that. So there were people doing stellar evolution and taught to do single stars and maybe binaries. And there's people that enjoyed throwing point particles around in the star cluster and looking at the dynamics. And there's different ways to solve this. In reality, both of these are stars. And so these point particles, they also evolve and interact with each other. And these evolutionary stars, of course, they have some dynamics, and there's often a third star. So this division is not so clear. But OK, so the first two channels, the first is the classical common envelope channel. And Ilya discussed this, but the trick here is to start so far apart that the stars have enough time to form a pretty massive core. And that overcomes the mass challenge. And the very last moment, they engulf each other's envelope and you drag them in. That's my one-sentence summary of the common envelope channel. And it could be back and forth and more complicated. But the trick is to start far apart and drag them in the last moment. The trick in the dynamical channel, I cannot surpass Ilya's way of describing this. It was this dating. So these are black holes. They form basically by themselves, and later by dynamics they find each other in the center of the cluster. And so that's only the start. We're a bit later, and people got creative, including Ilya and me. But there's many ideas now how you can bring them together. And maybe one to point out is triples, which is, I think, one of the most interesting one to be in between. That there has an aspect of dynamics, but there will certainly evolution play a role. We'll see some of these channels. I think my task was to discuss the chemically homogeneous channel. So that will be the rest of the talk. And so this is something I worked on in my thesis. And at that point, I didn't know about gravitational waves. It happens. And so it was a fun paper that discusses X-ray binaries, but we forgot this one sentence that this has implications for gravitational waves. I mean, you learn as you go. And so I learned from Ilya Mandel when I was a postdoc here in the US, close to the LIGO Center. And we were not very fast with this because it was such a weird channel. But then rumors started and we accelerated. And not only us, also Pablo Marchand, who is raised in the same group that I come from, in Norbert Langer's group. And we competed for the first paper, actually. But he deserves a lot of credit. And he has really been taking the detailed simulations for this. So we became friendly after. But we had an interesting time at the first start. So that's certainly a look at his papers. And I also want to credit Matteo Cantiello for the first part when we were still doing that in my thesis time. So let me tell you about this. So this goes back to people that didn't think about binaries, but thought about rotation. Because for a long time in the massive star community, binaries are too hard to do, right? There's too much free parameters. Let's just apply Occam's razor and decide we don't want to think about all this. But it turns out massive stars do many things that don't fit these single stellar models, and for a long time it was popular to think about what do rotating stars do. We see stars rotate, not all of them so fast, sometimes fast, but there's a long history of thinking about what does rotation do to stars. And one of the things it does, it flattens the star a little bit. And so the centrifugal acceleration towards the equator makes them a little bit oblate. And that has interesting consequences, at least we think. So let me show you this in the most traditional diagram that we have in stellar evolution, which we call the Hertzsprung-Russell diagram, at least a traditional version, the theory version of it. And so stars are born on the main sequence, born or start to burn hydrogen, and they're pretty small, but all stars expand. And so stars, I'm giving you stellar evolution 101, stars have a core that becomes helium-rich and contracts, and at the same time the envelope expands by many orders of magnitude. And so this is what evolutionary tracks could look like, at least ours. There's small variations here, how much mass loss, what is the composition, but in principle they expand. And so if you have rotation, this diagram can look very different. And so here's an artist impression of a rotating star, one that's rotating so crazily fast it's actually shedding material. We see such stars, they call BE stars or OE stars, and E stands for emission from a disk that is around these stars. And so these stars are probably a little bit flat, and so what happens is that normally stars are stably stratified in their outer envelopes, we think. Just the core is convective and bubbling and mixing. But it's, for a normal star, not possible to bring helium from the center to the surface. Unless maybe you strip off the surface in winds or something, but we don't want to do that. In these rotating stars, the poles are a little bit hotter than the equator. And so this creates an imbalance on equipotential surfaces, and this tends to trigger, this makes it possible for flows to start flowing, which we call meridional circulations or Eddington-Sweet circulations. And the simple estimates, ballpark estimates, the estimates would be that these are of interesting timescales for mixing material over the lifetime of a star, at least during hydrogen burning. Later in the life of star, the nuclear reaction rates, they speed up, and these mixing processes can probably not keep up. But during the main sequence, they can probably help to convert hydrogen from the surface, bring it to the center, connect it to the bubbling core, the convective core, where it can be burned. And so then something interesting happens. Oh, yeah, and there's a second type of mixing, it will be shear mixing, so different layers. If there's enough shear, you can have little eddies turning over. So what happens then is something funny. Initially, these stars are almost the same. So the blue lines are, they also start in the middle on this main sequence. And you see a small difference. You can see these blue tracks start a little bit to the right, and that is just the centrifugal support. So these stars are a little bit more bigger and less luminous, but then over time they start to burn. And so using these simple cartoons, we now burn the entire star into helium, at least in the ideal case where you would fully mix this star. And these particular models, it's pretty close to that. And so you get this little, where you see this little O sign, this circle, that is the new, that corresponds to this little hook that you see in the normal stars. That's the moment they run out of fuel, of hydrogen. And that's the moment when the star starts to contract. And so you also see that in the rotating tracks. And so they contract further to these little crosses. That is the point of most contraction. And these stars were not fully mixed. There was a tiny bit of hydrogen left in the outer layers. It ignited. And so you see some of these tracks turning around. And you see also a lot of fuzz. That is numerical issues with the model. So let's not worry about that. But the prediction here is that if you mix, you get mixed stars, and you convert them from hydrogen into helium, and helium just takes less space than hydrogen. Also has to do with the opacity, but I'm simplifying a bit here, right? We go from 4 protons to helium, that takes less space, and this contracts. So we can have a long, long debate whether these mixing processes are good enough, but if they are good enough, they will shrink, right? So this was originally proposed by Meder in '89, actually, to explain blue stragglers. For the moment, we don't think these mixing processes are enough to produce low-mass blue stragglers, but maybe in high-mass stars, these might be interesting. And so there has been a lot of interest in these for many reasons. And Stan also has worked on this. So people have thought of these stars, they're rotating and become very compact, and they're probably progenitors of gamma ray bursts, long gamma ray bursts. At least that's one of the suggestions. They're very hot. They may play a role in reionization. You might think you're looking at a POP3 star if you see one. Well, it's actually just a rotating star. And the yields of these would be interesting. So there was interest in the community about this. But it's, for now, I would say, still hypothetical. We don't have proof against it. And we have some interesting clues that this might be happening. But we don't have full proof that this is happening. But let's take this a little further. So what if you could achieve something like this inside a binary system, right? And so what happened to these stars? They were shrinking. Well, the size of a star matters enormously in a binary because the size will determine when it starts to flow material to the other star. And so this is what we are playing with in Utrecht with Matteo Cantiello. And so let's do the same cartoon here. This is from a conference proceedings around that time. This would be a hydrogen-rich star. If it's evolving normally, it would fill its Roche slope, also a lot of fun. But now let's assume that it's so tight in that binary system that the tides lock it, and it's rotating. That's how we thought of it initially. I think now maybe it makes more sense to think of it, it's just tidally deformed by the other star. But in principle, the cartoon still works. If this star would be shrinking, converting completely to helium, it would be a very compact star. And so from here, that's not the idea we had in the 2009 paper, but the step to binary black holes is very easy, because now we have two stars that are very close together already. Right? The separation challenge is full fit. And these stars shrink, and they're still at the right separation, like a few times 10, like 10 solar radii apart. These helium stars are so massive, it's very unlikely that the time the core collapses that these things can explode. So most of the material will probably fall into these black holes that you're forming. And these black holes are exactly at the right location that you need them for gravitational waves to do the rest within a few gigayears. And so these last sentences were not in the original paper, but that's what we realized when we talked to Ilya Mandel and Pablo Marchant have been pointing out. This is still the old, it's one of my thesis papers. This is one of the first evolutionary calculations of this. This is a star in a binary system. I only show you the primary star. And so initially, these stars start down there at 0h. And these lines, these gray lines are lines of constant radii. And so these numbers you see is 4.0 days. That is the orbit of the binary system. And so these wider orbits, 4 days, 3 days, let's go faster than I wanted. They evolve normally. They fill their Roche slope, as we all taught in Binaries 101. I don't think that's a course taught in many places. Maybe it should soon. In tighter binary systems, a 2-day orbit, 1.5-day orbit was the closest that I could converge at that point. I had stars that really went up and stayed almost at constant radius until my computation started at that point. And so from there, it's a small step to think that these would collapse. So Pablo Marchant has taken this further. Maybe the first question is, do such tight binaries exist? And yes, absolutely. We see them actually everywhere. And so this is one example. This is a postdoc, Leonardo Almeida, that worked with Hugues Sana and myself. This is one of the systems that we found in the LMC. And it's two stars. This is coincidence, but these both stars are basically 30 and 30 solar masses plus or minus 1. I mean, how close can you be? well, actually, I don't think that this particular one will make 2 black holes, because it is in a large Magellanic Cloud. It might make 2 black holes, but I think the winds will widen this particular system. But if we had a similar system, maybe slightly more massive at a more metal-poor galaxy, then it would be a good candidate, if you believe this scenario at all. So these systems do exist. And so this is also Pablo's credit to think of these systems if they are already in over-contact. These mixing processes would probably be stronger than when they're almost in contact. So that's for his credit. Oh yeah, and this looks way nicer if you show the 3D rendering of this particular system. It's just the artist impression. So the shape is really what we determined from the light curve and the spectroscopy. These solar flares are the freedom of the artist here. But we really think there's a bridge between these 2 stars, and they share, I forgot, 15 or 20% of their volume. They should be connected. This is not the only system that we know that is like this. We know a lot of these systems of solar-type stars, actually, but they're a bit different. We call them WUMA systems. For these massive ones, we have a few of them also in the Small Magellanic Cloud. And so for me, going after these systems and really seeing if we can get those parameters correct is one of the best ways to see if we can test this scenario. Okay, I can show you some predictions, but maybe I should, before I do that, I should hold here. So often this question comes up is, how many detections do we need before we know which evolutionary channel is right? And so this is stellar evolution. So these, with all respect, I think what we're talking about is more ideas or cartoon scenarios, in all honesty. However, as many CPU hours we threw at it. It's very simplified models with approximate recipes for the physics, and there's a lot of freedom there. And so one of the questions to ask is, what is really the predictive value of these models? And so I think we should not be asking the question, does it take 100 detections to say A, B, or C? These are ideas out there, and there's a lot of freedom. And so if you disprove the spins, one of us, or Vicky, or me, or one of our students will come up and find a way out, because that's the freedom we have in these models. And this is incredibly frustrating for physicists that think of a theory that should have testable predictions. But it's not the way it is. This stellar evolution is like weather predictions or something. We don't have the initial, well, it's not as bad as weather conditions. We can do, we can do much longer timescales, but either way. You would shoot at me if we didn't have any observable predictions. But we should really be looking for, is there some fundamental things in these models that will not change? Or is there a fundamental idea behind that we can find and test? And so for this mixing channel, do these mixing processes occur at any reasonable time scale? And maybe there's such a big difference between the channels that we can say something, but I think we have, for a long time, we'll have enough freedom in the models to tweak our way around it. If you tell us all these black holes are slowly spinning, we'll find a way to spin them down. I mean, in a way that is physically logical. That said, you would shoot at me if there would be no predictions, so here are some of our paper, but take them with a grain of salt because it's extremely simplified. The delay time for chemically homogeneous evolution, you see a shape here, don't buy the shape. But I do think that naturally, these chemically homogeneous models will give you things that merge within Hubble time. That is, if it works, that it will do. What the shape of this distribution is will be harder to say. You can think about qualitative differences with the other channels. The masses will typically be massive. I would say 30 solar masses and a bit up. And then it's stopped by the parent stability regime. That's what I would say. I think it will be hard to make lower mass events. I wish we had such confidence in the models that I could say that with certainty. If I really add extra mixing in these models, I can go to lower masses, but it is tough. So this homogeneous one is not, I don't think it's a channel to make double Newton stars. The rates, we can produce the rates, but I mean, yeah, it depends. We have enough freedom to get the rates. The rates at this point are not very distinguishing between the simulations. That is, let me wrap up here. How do I wrap up? So I think the way to go is to go for the things that fail to make binary black holes. Right? What are all the side products? if we want this physics to work for rotating stars and for these closed binaries, there will be a lot of systems that would almost make two black holes but just fail. And I'm going to skip quite a bit from here. And let's see if I can do that more efficiently. This way. So one of the ways to fail is if one star explodes, but it tends to shoot out the other star. Actually, the compact object disappears, but the second star was going around this compact object, and suddenly it has no friend anymore, and so it will continue in a straight line. And many people call such systems runaway stars. What we predict is that they're pretty slow. I would call them walkaway stars, but it's a different story. This is one of the studies. I think this is where Gaia is going to help us understand binary black holes. Because this is the stars that fail to stay with their companion, right? And that's an idea that has been proposed by many. We were smart enough to do this the day before the Gaia release came out. So we have a whole suite of models that we should be able to compare with. And maybe so if these systems don't have the right masses or the right mass ratio, we can make a lot of other interesting things. And Pablo Marchand has been pointing this out. There is some area of the parameter space that if we do make binary black holes, if they're lower mass, we would have this contact binary still that we can look for. If they're not equal masses, we think they should make ultraluminous X-ray sources. So one star goes homogeneous, makes a black hole. The second star is low mass, it wants to swell up. And so it starts feeding this black hole at a very different rate. These systems, they should be there. If you want to make A, you have to also make B. And then there are the parent stability supernova. We can't overproduce the rates. If you make these really heavy cores that make binary black holes, if you make them just too massive, you would have a parent stability supernova event. If they are very bright events, we should be able to count them. And there's some constraints coming from the rates for each parent stability supernova. We know how many stars die in this upper part of the diagram. And I think I should leave it like that if I want to be friends with our chair.
You've preempted my question already by saying that you can get around anything. But
that's not what I said, but go ahead.
With stars that are rapidly rotating and a lot of tidal interactions, don't you really expect large aligned spins for the black holes, which is precisely what's been ruled out already by the KF measurements?
I would have said that before the spin measurements came. Absolutely. And honestly, if we could rule out this, I would be equally happy. I mean, I like this scenario because we proposed it, but I'm not married to it. So I would have thought this would lead to large spins. If we talk in detail, okay. If we talk in detail and think about it, in the late stages of the evolution of these systems, when they're Wolf-Rayet stars, they can still have winds which substantially spin them down. If you do that without widening the binary system, which is completely allowed, then we can reduce the spins quite a bit. Whether the spins are exactly aligned or can be tilted a little bit, that will have, there are open problems there of how we convert from stars to black holes. I don't have a model that has the predictive power to give you the spins and that we shoot out this model with absolute certainty. On the other hand, if you had asked me before knowing the spins measurements, I would have put my money on high spins. That is indeed true. But I don't think we have the power to exclude it at this point.
Hi, good talk. So Eddington's sweep circulation scales with the Kelvin-Helmholtz time times a rotational velocity squared. It's clearly not, we're not getting chemically homogeneous mixing for most stars, clearly. So there's more massive stars mix easier. Is there a lower mass you have in mind where this might work and where it might not work?
So for binaries, single stars, if you have a funny way to mix them as crazy, you can go lower mass, but these binaries, they also still need to fit inside an orbit, and you cannot put them infinitely close. So there's a relation between how fast they rotate and how close they are. And so I would say the lowest we can do is 30 solar masses for the stars. What that means for black holes, that depends a bit how much mass you lose on the way. That is for the mixing we currently assume, but it will be tough to do this for stars born.
Masses initially and then mass loss.
Initially, yeah. So with some mass loss, or if we have more efficient mixing, maybe we can push this down a bit, but I don't think we're going to make double neutron stars out of this. Let me put it that way.
No, but could you make 15 solar?
If I push within the freedom that I have, I could allow that in the models, but it's not what I would use as default assumptions.
So, if I understood correctly, you form the two black holes, and then you wait a couple of giga years, and they merged. Now I know you don't like the prediction business, but does your model give predictions, or what are your model's predictions of the separation distribution and eccentricity distribution? And yeah.
The separation distribution, yes, if I assume that so the uncertainty there is how do winds take away angular momentum from the system, but we can make reasonable assumptions there. I think we should do better than we do now, but separations I can do. Eccentricities, then somebody needs to tell me whether I have any form of kick at the moment these black holes. If you give me a recipe, I'm happy to give you an eccentricity distribution that comes out of it, right? And that's the type of games we play. We think of reasonable recipes and see if we can exclude A or B. Separation eccentricity was another parameter you thought of? That's the two? Yeah. Yeah.
Yeah, so I guess I have a related question. So even at the qualitative level, your time, I'm interested in your time, merger time distribution. So it looks peaked. Do you think that peak will survive? Do you think it's peaked generically, qualitatively? It's not 1/tau compared to the standard, binary evolution expectation?
This is from our paper, and the assumption I would improve now is how winds take away angular momentum. We need some more fancy 3D simulations to see if the winds have similar speed as the stars going around each other, how much angular momentum do they take away?
Yeah, that's a tough one. Slow winds, secular evolution of the orbit with slow winds is not...
So I don't know how much freedom I have if that happens. Then I would increase the number of short delay time systems. I cannot do the population synthesis by on the spot here. Yeah.
So I had a question on that interesting binary you showed, LMC, right?
Yeah.
The 28 plus 28. So where in the evolution is it, in your opinion?
Well, that's the most exciting thing. It's in 30 Doradus, which is a young region, but it's not sitting in the youngest part of it. It's just sitting in the field of 30 Doradus. And most stars there are 3, 4, 5 million years old. Yet, the age you infer for this is basically 0. If you look at the parameters of these individual stars, compare with single star, non-rotating models, you would infer a very, very young age. Now, what is the solution? And they're too luminous. If you're not fully following, we should probably not compare with single stars and non-rotating models. This is probably the best indication. If you have this mixing, things tend to look younger and be overluminous. And so we don't know precisely the age of the system. I would say it's a few million years old, and it only looks like it's just born because it has been mixing. That is what I hoped. We just have UV measurements of the surface abundances, and I would have said nitrogen and helium would be at the surface. We don't see that. So the puzzle is not done here yet. Okay. We have a few more systems where we can play this trick. So,
But in that picture you are presenting, this system was born as a contact binary, or did it come into contact? Don't know. Okay.
I don't know for this particular system. So there's many interesting papers that are discussing how do you form these close, not as close as this. I mean, we don't even know how a 10 or 100 day binary period form. And so one of the ideas that Smadar probably likes is that a third star helps there, or that these stars form inside a disk and migrate, but the simulations that are out there, they don't have the resolution to make these super tight systems. A long time ago, people thought about very fast rotating stars that split, which Abi has had some entertaining ideas about as well, but that doesn't seem to be popular anymore these days.
Do you have a question? No. Neil? No? Okay. Ilya has a question.
It was more of a corollary to Stan's question. So I was wondering if you could actually use the existing LIGO observations to place a limit on how low you can go with this channel. Because I think if you go too low, in terms of masses, there are so many low mass stars around, and this channel would, if it generically worked for lower mass stars, you would see many, many more systems merging in the LIGO data set. So could you actually go the other way and place an observational constraint?
I'm not so convinced that the common envelope channel fully works for these high mass stars. So I think for Newton stars, that's our best shot. But if we talk about stars over 30, 40 solar masses, I'm not so convinced that that's the channel yet. So let's say that's out of the window, and you're allowed to make all the binary black holes that we see with chemically homogeneous evolution. Would you overproduce them? I thought they sort of follow an IMF, right, at this point. So I think we'll be fine.
Last question.
So Selma, so a question on the high mass end. So if they go through this chemically homogeneous channel, they become Wolf-Rayet stars, so they get mass loss of a few times 10 to the minus 5 solar masses per year.
The trick is you do this all at low metallicity.
Okay, so that was my question. You have to suppress the mass loss rate, or you will not get 30 solar mass cores at the end to form the high mass.
So actually, for single stars, if they have a mass loss rate, then they spin down and they don't mix anymore. These binaries, they don't mind spinning down because their spin is replenished by the orbit of the other star, and that's like extreme amount of angular momentum for these stars. So they keep being tightly locked. The problem with mass loss is that if these winds are fast and they leave the system quickly, what it does, it widens the system. Widening means that the period goes down. Period going down means both they spin down and and the wider they are, the less deformed they are. So for these binary systems, we want low metallicity because we want these systems to stay very close and tight. And the spin is not so much the issue.
So there is a threshold, there's a metallicity threshold where you won't form the highest mass black holes.
Yeah, actually this homogeneous evolution we do at every metallicity. It's just at high metallicity they would widen too much. If there is a secret way to shrink them again, well, let me just write that paper first and then we discuss.
So Avi, do you have any announcements?
No, we are gathering tomorrow at 9 a.m.
Okay, so tomorrow 9 o'clock we'll continue with this same session, starting with Fred's talk. Let's thank Selma and Ilya and close for the day.